VSEPR theory allows us to predict the shape of molecules. Let's remind ourselves what it stands for. Valence, shell, electron, pair, repulsion theory. So remember, what it's telling us is that regions of negative charge, so electron groups, will arrange themselves to be as far apart as possible from one another because negatively charged things will repel each other, right? Opposites attract, like charges repel. So remembering that bonds are made of electrons and lone pairs are also electrons, those are all negative things. So they will all arrange themselves to be as far apart as possible from one another. So to use VSEPR theory, we have to count how many regions of negative charge we have on the central atom and then use geometry to arrange them as far apart as possible from one another. Now, the thing to remember with VSEPR theory is that one electron group could either be a single bond, a double bond, a triple bond, or a lone pair. So if we look at this molecule here that we just drew the Lewis structure of, we'll see that it contains 2 single bonds and 1 double bond on the central atom. So because carbon is the central atom here. So in terms of the number of groups on that central atom, it has 3 groups. Now, if we were counting pairs of electrons, it would have 4 pairs, right? Because that's 2 pairs. Or if we were counting individual electrons, we'd say it had 8 electrons. But we're counting groups of electrons. So this has 1, 2, 3 groups, or 3 regions of negative charge on that central atom. Water has 2 single bonds and 2 lone pairs on the central atom, so it has 4 groups. Let me just quickly draw a Lewis structure for you. SO2 down here, I don't know if you can see, that's a lone pair, has 1, 2, 3 groups on the central atom, a single bond, a double bond, and a lone pair. So that's 3 groups. Okay, so let's take a look. In fact, let's use those molecules as our example. Say we want to determine the shape of a water molecule. We start by counting the number of groups on the central atom, which is 4. So this is for water. It's got 4 groups on the central atom, and 2 of them are lone pairs. Okay, so 4 groups on the central atom will arrange themselves to be as far apart as possible from one another. And the geometry that gets them as far apart as possible is this geometry. It's called tetrahedral. So these 2 bonds are in plane with the page. This one's sticking out, that one's going in. So there's the 4 groups on that central atom there. We call that tetrahedral. And that represents the electron pair geometry. Now, if I want the actual molecular geometry or the shape of the molecule, I need to cross out my lone pairs and redraw. And now I have a shape that is called bent or angular, and that is the shape of a water molecule, okay, because it's got 4 groups on its central atom, 2 single bonds and 2 lone pairs. The 2 lone pairs influence the molecular geometry, but when we talk about molecular geometry, we don't count them, okay? So this is the electron pair geometry, which is tetrahedral, and this is the molecular geometry, which is bent. Let's do our other example. Okay, so formaldehyde has 3 groups on the central atom. Remember, we're really just concerning ourselves with the central atom, so it doesn't matter what's going on with the terminal atoms. We've got 3 groups on the central atom and no lone pairs on the central atom, so no lone pairs. Okay. So to get the electron pair geometry, we have to think, how would 3 groups of negative charge arrange themselves to be as far apart as possible? And it will be in that shape. Here's our central atom, and the 3 groups, the maximum distance those 3 groups could be apart is in this geometry, which we call trigonal planar, or a flat triangle. Now, because there are no lone pairs on that central atom, the molecular geometry will be the same as the electron pair geometry, and it will also be trigonal planar, or a flat triangle. Now the bond angle, the angle between those bonds, is going to be about 120 degrees because that's the maximum distance that three things can be apart from one another. Take a circle, which is 360, and divide it by 3. Which reminds me, we didn't talk about the bond angle up here. The bond angle in a tetrahedral is usually 109.5 degrees. When you have lone pairs, your bond angle is actually less than 109.5 degrees because the lone pairs actually occupy more space than a bonding pair and are actually pushing down and forcing those two bonds closer together. So it's actually less than 109.5 degrees. Okay, let's do one more. Our other example was SO2. Okay, so here we've got SO2. It's got 3 groups on its central atom. 1, 2, 3, and one of them is a lone pair. So 3 groups on the central atom, and one of them is a lone pair. So remember, maximum distance apart that 3 groups can be is in the trigonal planar geometry. That's the electron pair geometry. But are any of them lone pairs? Yep, one of them. So get rid of it, redraw. And the molecular geometry will be bent or angular. Now, when we looked at water, the bond angle in the bent water geometry was less than 109.5 degrees, but it was a derivative of the tetrahedral geometry. This bent geometry is a derivative of the trigonal planar, and so its bond angle is less than 120 degrees. Okay, let's do one more. Carbon dioxide, I'm going to draw it for you since we didn't do that Lewis structure yet. Okay, there's its Lewis structure. It has 2 groups on the central atom and no lone pairs. Okay, so it's 2 and 0. So its maximum distance apart that 2 groups can be is in a straight line, right? So its electron pair geometry is linear. The angle between those bonds is 180 degrees. Because you know there's 180 degrees in a straight line. We have no lone pairs on the central atom, so the molecular geometry is the same. So it is also linear. Remember, that's the condition. To have an identical electron and molecular geometry, you have to have no lone pairs on the central atom. If you do have a lone pair on the central atom or 2 lone pairs on the central atom, your electron pair and molecular geometry will be different.